Hello and welcome back to stage one at Apidays Helsinki and North. And now we're starting our security track today. And we are starting with Michał Trojanowski from Curity. And funnily enough, we were just talking with you, Michał, that I've probably met more Curity folks live than you have. So kind of
Yeah,
funny.
thank,
You have been
thank.
working there 2 years now.
2 years almost. Yeah. But
Yeah.
obviously, thanks to the pandemic,
Pandemic.
yeah, I haven't been able to meet anyone in person.
Yeah. No, we live in a very weird time right now, but I'm glad that you're here and we have other fintech topics on the stage two track. So if you are really into fintech, you can jump there after this. So let's go and continue with the presentation. I have your slides here and everything looks fine.
Yeah, thanks. Welcome everyone. So my name is Michał Trojanowski, and I'm a product marketing engineer at Curity. And the topic for today is financial grade security for APIs. So what can you do to give your APIs that level of security that is used in fintech? So I'm glad actually that Marika touched the subject that if you're into fintech, then you should definitely listen to some other stuff that we have here on the conference. But I would like to tell you why I'm speaking about financial grade and how is that a bit maybe different from fintechs. And of course, the topic of security is very vast, and the things that you can do to upgrade security in a financial grade API is also very vast, and there are a lot of things that you can do. But I would like to focus on a few things here today, and I would like to show you a few features that you can use in any APIs to make your security a bit better. So, and these are the things like MTLS and sender constraint access tokens, and then some features around auth flows, mainly PAR and charm. When we think about financial grade APIs, and when we see that name, we think almost instantly we think about finance, and we think about fintech. We think about that payment APIs and APIs exposed by banks and so on. But important thing to remember is financial grade doesn't mean that you have to deal with finance. So you can, for example, have medical APIs or APIs which deal with sensitive data, or even just your own regular APIs, which you just want to secure in a better way, to secure with features that normally banks use or the financial apps use. And that's why we talk about financial grade and not financial APIs, because this can be any API, but you want that security to be the same level as in a financial institution or in a financial API. And even if you look at the OpenID Foundation, the profile from the FAPI group, so it's not about financial API security; it's the financial grade API security, and it shows you those different features that you can use in your APIs, even though you're not in the finance sector. It's just features that help you upend the security. So let's start with MTLS. The name TLS is probably familiar to most of you, and you know how TLS probably works. So when the client connects to the server, not only the connection is encrypted, but what is important is that the client is able to identify the server, to authenticate the server. So the client has the certainty that it connects to the right server, to the one that the client really wanted to connect. The server, on the other hand, doesn't care about the client. It allows any client to connect. And what is important is just that the client knows which server it connects to. So in MTLS, which is not a mini version of TLS, it's mutual TLS. Both the client and the server, so both parties are interested in authenticating themselves. So now not only the client has certainty about the server, who the server is, now the server also knows the identity of the client. So the server is able to identify the client through a set of certificates, and the server can limit the list of clients which can talk to some endpoints, and it knows who the client is through that MTLS connection without any other authentication mechanisms. And this feature per se is can be used in many different scenarios. And in fact, it's used in different scenarios. And one of those scenarios is sender-constrained access tokens. When you think about access tokens in APIs, most of the time you use bearer tokens. But you have to remember that there is this other type also, the tokens which are sender constrained, or we sometimes also call them proof of possession tokens. So what's the difference here? Bearer tokens are a bit like cash. The receiver, the API gateway or the API, doesn't care who the token really belongs to, right? So if I have client 1 and that client was issued an access token by the authorization server, and now it sends it to the API will verify the signature, will check the expiration of the token, and if that's okay, then it will send it to the API. But now, if client 2 gets hold of the same access token, maybe legitimately, or maybe it's a malicious client, that it doesn't matter, it can send it to the API, and the API again verifies whether the signature is okay and whether the expiration time is okay, maybe some claims inside of the token and so on, and sends it to the API. It doesn't care that it now comes from a different client, and that's how the bearer tokens work, and that's usually how cash works, right? So the guy in the store doesn't care who came with the cash. And proof of possession tokens work a bit more like credit cards. So now the receiver has to know the identity of the client to check that they really can use that token. And when you come to a store with a credit card, they should maybe they don't, but they should verify if it's really you, if it's really your card. So now if I have a client who was issued a access token by the authorization server, that client sends the token to the API gateway together with a proof of possession of that token. And now the gateway verifies not only the signature and expiration time and so on, but it also verifies that that client is in the possession of that proof and can use that token, and only then it's sent to the API. If another client would get a hold of that same access token and send it with a different set of credentials, different set of a proof of possession, maybe different certificate or something like that, then the API gateway would reject that token, even though it's a valid access token, right? The signature is okay, the expiration time is okay, but it's not, the token doesn't belong to that client. If a client would send it without any proof of credentials, then obviously the API gateway would also reject such a token. Proof of possession can be implemented in different ways, and one of those ways is a standard defined in RFC 7800, and it's a proof of possession for JOTs. The standard adds a CNF claim, confirmation claim, to the token, and that claim enables the recipient to verify the caller. So let's see how it works. Now we have a client with a public key and a private key, and that client, when it talks to the authorization server, asks for an access token. It sends the public key together with a proof of the private key. And here we can use that MTLS connection that we talked before. So MTLS gives the authorization server that proof that the client is in possession of the private key, because that MTLS session could have been established. The authorization server sends back an access token with that CNF claim, and this claim can have a few different formats. It either can be the ID of the certificate, or it can be the fingerprint of the certificate, and there are a few different formats there. But the important thing is that CNF claim, that information about the proof of possession, is embedded in the token. And now when the client wants to call an API, it sends the access token together with that proof of possession. And again, we can use that MTLS connection here. And again, the API gateway, thanks to the MTLS connection, is able to verify that the client is in possession of the private key. And now it verifies not only the signature and expiration, but also verifies that the embedded information about the certificates in the token in the CNF claim are the same as the certificate used in the MTLS connection, and only then it will allow that access to the API and forward the token to the API. So you would use this scenario when you're worried about tokens being stolen from your client and used in your API to call your API with a token which doesn't belong to that client. That POP for JOTS is one implementation. It has this limit that here we're using MTLS, and not all clients will be able to use MTLS. For example, if you have an SPA in the browser, you won't be able to make an MTLS connection to an API gateway or the authorization server. So there are different implementations of the POP tokens. For example, there's a demonstration of proof of possession. You can have you can use that if you have a client which is not able to hold a secret, so to establish an MTLS connection to servers. But let's move on to PAR. So PAR stands for Push Authorization Requests. And again, it's a standard defined in RFC 9126. And this one deals with authorization requests, with auth authorization requests. And it provides means for confidential and integrity protected requests. How does it work? Let's see again. Let's see at first how the standard authorization request looks like. So the client sends a GET request to the authorization server. It sends a bunch of parameters in the URL, and the authorization server processes that request, authenticates the user, maybe asks for consent, and then sends back a 302 response with a location header and the code, authorization code in it that can be exchanged for a set of tokens. But there are a few problems with this flow. First of all, the authorization server has no way of identifying the client during that request. The authorization server uses redirect URIs, or the auth flows use redirect URIs to be able to make sure that the response is sent to the legitimate client. That's why it's so important that the client registers the redirect URI before and then uses only the registered redirect URI. But even though the request itself is not authenticated, so the authorization server has no means of telling if that request really comes from the legitimate client. Through the redirect URI, the response will probably end up with the legitimate client anyway, but maybe we don't want to allow other clients to be able to start that authorization request. The authorization server also can't say if the parameters are okay. Of course, it can validate the parameters, meaning that if the scopes, if it doesn't know the scopes, or that client ID is not allowed to use those scopes, it can return a 400 response. But the authorization server can't verify whether these are really the parameters that the client sent, that the client wanted to send to the authorization server. That request goes through the user agent, and the user agent is a hostile environment. And if you have a man-in-the-browser attack, then someone can tamper with the parameters. They're not encrypted in the browser. So the authorization server can't be sure if these parameters are really the parameters that the client has sent. And also because, again, because it goes through the user agent, it's not encrypted end-to-end. These parameters can end up in the logs. For example, they can be read by an attacker, and also, you might run into a problem where you have a really long authorization request with many different parameters used, and you can maybe hit some limits for the URL length in some browsers. So that can also be a problem. And all those problems are addressed by push authorization requests by PAR. So how does it work? When the client wants to make an authorization request, it first makes a post to the PAR endpoint of the authorization server, and it sends all the parameters that would be used in the authorization request in the body. And what is more, the client authenticates during that request. It uses the same authentication method that is used for the token endpoint. So if the client uses a secret and has to use basic authentication to the token endpoint, it would in the PAR endpoint, it would also use basic authentication and send the credentials in the authorization header. Now the authorization server authenticates the client, so knows exactly who the client is, can verify the parameters. Because we have a confidential client, the authorization server knows that the parameters haven't been tampered with, as the authorization server is sure that the request hasn't gone through a browser, because we need a confidential client for that, so it has to be backend to backend connection. So it knows the parameters are okay. It can validate them, authenticate the client, then save the parameters somewhere, and send back a request ID to the client. And now when the client wants to authorize, it just sends the request ID to the authorization server, and the authorization server takes all the parameters from the database and uses them in the request, in the authorization request. So what PAR gives us, again, the client is authenticated before the authorization request. The authorization request parameters can't be tampered with because we have end-to-end encryption all the way. The parameters do not traverse through unsecured transport, so they can't end up in logs or be read by a man in the browser attack. The URL limitations are no longer a concern, and what is more, the authorization server has an ability to ease the restrictions on redirect URI. For example, the client might want to use some redirect URIs for tenants, want to use different subdomains or different URL prefixes, and because the PAR request is authenticated, the server knows that the parameters haven't been tampered with, and knows the client, and that's why it can allow some different redirect URIs, different from those that were pre-registered in the authorization server. So PAR deals with authorization requests, and JARM, on the other hand, deals with authorization responses. It stands for JOT Secured Authorization Response Mode, and it's a draft specification from the OpenID Foundation. It's still in draft state, but it's actually recommended by some of the FAPI profiles, and it's implemented by a few of the different authorization servers out there. So I think it's safe to use that specification anyway. And this one protects against attacks on the authorization code response. So again, let's have a look at how the standard response looks like. So the client makes a GET request to the authorized endpoint, and it gets back in a 302 response with a location header, and there's the code and state, either as query parameters, fragment, or form posts, depending on the response mode used by the client. Again, this has a few problems. First of all, the client doesn't know which authorization server issued that response. That is a problem if the client is able to talk with a few different authorization servers. Then when it gets back this response, this redirect, it doesn't know which authorization server has issued that response. And this can lead to what we call mix-up attacks. What is more, the client doesn't have any way to check the integrity of the parameters returned. So maybe an attacker has changed the code for a different one. So the code, it can even be from the it could be from the legitimate authorization server, but it could come from a different transaction. So it's not from this state. and the client has no way to verify that. And again, this response goes through the user agent, which is not encrypted, and a man in the browser attack could tamper with those parameters. So JARM tries to respond to those problems. And now in the JARM mode, the authorization server responds with a JOT in the location header, and the client can verify the JOT, decode it, and all the information it needs from the response are in the JOT. There's also the issuer claim, so now the client can verify which authorization server issued this response, and it knows that the code and state haven't been tampered with because it can verify the signature of the JOT, so it knows that the parameters are okay. JARM supports all the usual response modes that we use in OpenID, so query, fragment, and form post. We just add .jot. We can also use that JOT response mode, which uses the default one for the given grant type. For example, if you use authorization code, the default is query. Default response mode is query. So in a JOT response mode, you would use it would assume query.jot. And again, what JARM gives us is that the code response is integrity protected. The parameters are strongly coupled, so it mitigates replay attacks and gives protection from mix-up attacks because the client is able to verify the issuer of the response. So key takeaways from this talk: first of all, don't discard topics which are labeled with financial grade only because you're not dealing with finance. Financial grade means that it's the same level as the finance industry would use, and maybe it's something that you want to implement in your API or in your app because it will give you that better security, and maybe it's not that complicated to implement it anyway. Remember those sender constraints access tokens if stealing the token is what troubles you. And give PAR and JARM a try if you're concerned with some attack vectors, again, authorization requests and responses. And again, these are not complicated to implement, so this might be something that can help to make your security better in this area. And that's all from me. Thanks.
Thank you so much, Michał. And I know that there was some heavy stuff in this talk. You basically ripped apart everybody's argument that they have and said, yeah, no, you're not doing this right. But good thing is that the audience is still alive and asking questions. So we have two questions at least. How often API security or access control have been implemented as part of an IAM solution, and then another one, can POP be stolen or forged like token?
Can you repeat the first one?
Yeah, the first one was how often API security and access control have been implemented as part of an IAM solution?
Okay, so as I said at the beginning, API security is a really vast topic, and there are things which concern your API security but are not part of your API implementation. So, for example, those center constraint access tokens, it's something that you would implement on the authorization server side and the client side, but it makes your API more secure because you have more control over who is calling your API, right? So if someone steals your access token, they won't be able to use it to call your API. So even though you haven't implemented anything in the API, then it still gives better security. So I wouldn't say that you would implement things that relate to API security in IAM. These are features that are part of IAM or part of auth flows, but they can help you with the security of your APIs. So things like PAR and JARM are this example. They were made to make the security of the auth flow better, but at the same time it gives you better security of your API because you have less possibility for an access token to be stolen or
yeah, I think it's like, in a very simple terms, you have to have API security like inbuilt with the IAM, with the gateway, with the actual implementation with the API, and all these need to talk sufficiently to each other, basically with the
Exactly.
job tokens and the proper requests and responses. Good. Maybe you can really quickly say something about this can pop be stolen or forged like token question, or maybe you can answer at length.
I would say yes, it can if someone can steal that proof of possession. So if it's a backend client which now communicates with the API and with the authorization server, and you have that proof of possession baked in the backend client, it's really much more difficult to break into your backend client and steal that certificate, so that someone who steals that token, so that they can still use it, and call your APIs. Because that token maybe is flying around the internet somewhere anyway, and maybe someone will be able to intercept it, but they won't be able to, break into your network and steal that credentials from your network to be able to call your API. So, well, of course, yes, it is possible, but it's much more secure than with bearer tokens.
Yeah, it's like the public-private key basics of it.
Exactly.
That you have a shared secret. Great. I think I even managed to get something what you were talking. Perfect. Hopefully the audience did too. So thank you, Michał.
Thanks.
We'll welcome the next speaker on